Hey guys, here we are wrapping up chapter 14. We're going to look at section 5, Geological Hazards. It's a little bit of an oddity, if you will, for the chapter. We've really been talking about minerals and mining, etc. Here we're going to look at the forces of the earth. So it's kind of a best place to fit it, if you will. But we're kind of departing from getting minerals, what they do, economic effect, environmental effect, into geological hazards. Largely, we're going to talk about earthquakes, volcanoes, tsunamis. So these dynamic processes that are happening in the earth, and then they also lead to things like erosion, landslides, what have you. All right. The earth beneath our feet is moving. Just like mountains are constantly being pushed up, well, the ground underneath our feet is actually constantly in moving process. It's broken up into the tectonic plates. We have large tectonic plates that both our continents and oceans sit on. The asthenosphere, the very kind of top part of the mantle, it's kind of this pliable, plasticky layer, and this is what the plates float on, but they're moving around. It's slow, but they're floating on this asthenosphere. Now, the geological activity that takes place at these boundaries largely occurs in three distinct patterns, if you will. So we'll throw the picture up here so you can kind of take a look at them. So we see the big picture of the world map. Well, these are the plates, and I'm kind of going to go from left to right, if you will. On the left, we have the big Pacific plate. Of course, it's on sort of both sides of this map, being the world. We have the Pacific plate, then they have the Nazca plate down below in South America, right in the ocean, but right up against it. We have the big North American plate, then we have the South American plate, we have the African plate, from the Atlantic all the way including Africa. We have the Eurasian plate, all of Europe and Asia into one, the Indian Australian plate, and then there's the Philippine plate up there. Now there's a lot of smaller ones, like we have the Caribbean plate kind of right below Florida, but between North America, South America. Once again, there's a lot of smaller plates as well, but these are the major ones. Now at all of these boundaries, one of three things is basically happening. We either have a transform fault. So down at the very bottom, that's one on the far left, where they're moving side to side. We have a convergent plate where they are colliding, they're pushing into each other. And in a convergent plate, one plate tends to subduct under the other. So that's what we're seeing. As they meet, one goes down underneath, and we get mountains forming up here, and this one gets pulled back down to the core of the earth in the massive rock cycle. And lastly, we have divergent plates, plates that are pulling apart. So down in the mid-Atlantic ridge between the Americas and Africa, Europe, we have a divergent plate. They're pulling apart. In the top part of India there, where we have that Indian Australian plate is pushing up into the Eurasian plate, and we get the Himalayas where they're converging and pushing together. And then along the California coastline, the San Andreas Fault is a transform boundary. So we get all three of these and some little bit of mixes, but they're the big ones that we'll talk about. So like the picture up here, here is the San Andreas Fault, and it is a transform boundary. As these plates grind and slide past each other, it creates earthquakes. And this fault runs almost the entire length of California, and you can kind of see that picture of it, if you will, off to the right, what it looks like from the air, because those plates are constantly in motion, and it's grinding the rock in these huge tectonic actions, making earthquakes up above. Also, we get volcanic eruptions. Now, we get volcanic eruptions where we get divergent plates, where they're pulling apart because the magma seeps up and billows out. But we also get them in areas that we call hot spots. Magma Once again, hot rises. Doesn't matter if it's hot air, hot water, or hot rock. Molten rock is hot and it's less dense than cool solid rock, and it slowly rises up through the mantle and reaches up into the lithosphere. And we get one of these hot spots, it pushes up, and eventually it reaches the surface through a crack, some sort of fissure in the lithosphere. So this magma erupts, and then we call it lava. Same stuff, it's just a matter of its location. And then it pours out and we get hot ash. Gases from the core get released up into the environment, and these volcanoes can form very majestic mountain ranges. A lot of those up in our Mount St. Helens, the Pacific Northwest, they're formed from volcanoes. And also the Hawaiian Islands were completely created this way. So that's what the picture is sort of showing. We get the volcano erupting, but over time the magma cools, and we get this island, this very mountainous, hilly island area. So they can make majestic mountains, they can make island features, this wonderful life, if you will, but they also can cause massive destruction. You know, once again, when they come up out of nowhere and then we get a new island, it's kind of like the creation of something wonderful. If people aren't around, we get this amazing mountain, and the ash actually winds up making really good plant growth, and it helps the soil. But when they erupt and people are actually around, or any living thing, then they cause massive destruction. They can obviously burn out the trees, kill off animals, habitat destruction, the whole 9 yards. So volcanoes are a bit of both, a little bit of creation, a little bit of destruction, all at the same time. Now, when we have earthquakes, once again, we can get earthquakes where plates are grinding together and they have to fall, where they rub apart and then break together and cause crumbling. And even when they pull apart, we would more get mountains or lava mountains that divergent, but the convergent and transform, we definitely get earthquakes. This is just that breaking and shifting of the rocks occurring at a fault, and they give off seismic waves. The seismic waves are the vibrations in the crust that we can feel. If the vibrations are strong enough, you know, we feel them, it rumbles and shakes. If they're violent enough, it can cause buildings to break apart, crumble. The ground, the dirt can literally liquefy from it shaking, just like you take sand and shake it, things sink into it. They can be enormous destruction, anything from, ooh, I think I felt a shake, to buildings collapsing around you. Now, a few things we'll talk about. We talk about the seismic waves or earthquake. We'll talk about the focus. This is the origin of the earthquake, ground zero, if you will. You know, where was the focal point? We'll talk about magnitude. Magnitude is the severity of the earthquake. You know, how strong was it? How much energy was released? And we can talk about amplitude. This is the size of the seismic wave. We talk about a wave. Amplitude is the height from the midline to either the crest or to the trough. When we talk about amplitude, the greater something's amplitude, the more energy is involved in that wave. So when we talk about our waves, we tend to use the Richter scale. The Richter scale is designed to measure the magnitude of an earthquake, and we do that by measuring its amplitude, the power behind the wave. Now, the Richter scale can start all the way down at 0, if you will, nothing's going on. When we're talking about earthquakes, though, we really don't mention them till they really hit around the level of 4. Earthquakes are recorded at 2, 3, less, but when you get it up to the Richter scale of about 4, then we have what we might call an insignificant earthquake. When I lived in South Carolina, we were in an old fault zone area up at the Appalachian Mountain area, and we would get earthquakes, but ours were never big. They were in this insignificant range. We had some that measured in the 4 and 4.2. I only remember feeling 2 of them, and they really were very minor, almost like a truck driving by. You just got this, like the china cabinet rattled a little bit. So insignificant is below 4. Minor earthquakes are between 4 and 4.9, 4 to 5, if you will. Truly damaging earthquakes move into the 5 to 5.9. So in the 5, we're going to get some definite damage. Things are going to fall off shelves, things may fall off in your house. We're going to wind up getting some damage. The house may get some damage, depending on how well it's constructed. You get in the 6 range, these are destructive. Now, once again, the closer you are to the focus, the epicenter of the earthquake, obviously the greater the damage you're going to have. Because you could be near a 6.0, but if you're 20 miles away, it really may be more like a 5 where you are, and it was a 6 here. So, you know, the energy gets expended and it loses some power as it moves away from the epicenter. But anyway, 6 are destructive. Major earthquakes are getting in the 7 range. And if it is over 8, we just refer to these as great. These are massive. They are unusual. The largest ever recorded, I knew you would ask. You always want to know. 9.5 in Chile, along the Andes Mountains, along the fault line there. In Chile in 1960, the largest recorded. Not that it was the largest ever in the history of the planet. We've only been recording these things for so long. But these earthquakes, as we look at, so when you look at the picture up here, it's just showing, you know, here's the focal point. That's where that boundary is. You can see the kind of shift in the plates there as they move up. Kind of what happens is one plate is moving up and there's a gap down here, and eventually all this earth and land above it causes that gap to snap and the rock snaps. And once that happens, then all the ground above it settles very quickly. It's actually a very slow process. It's moving and moving, but then all at once the big plate snaps and all that ground settles very quickly, and that's our earthquake. The longer or the higher this gap gets, the greater the magnitude of the earthquake when it occurs. Or if it's transom, it gets and it's pushing and pushing and pushing, and eventually it snaps off. So the pressure builds and builds and builds, and it eventually has to get released. The longer we go between earthquakes in a fault area, the bigger the earthquake will tend to be when it finally occurs. But they can be very damaging, just once again, depending on where you are, where the earthquake is, all these factors. Now, in the United States, we're looking at the map here, like we're talking about with earthquake risk factor. We notice all along the western coast, well, it's right on that transform binding, so they have the highest risk. Now, also when we move inland a little bit, we get up in the Yosemite in that area, and that's a huge cauldron where magma is pushing up. We have volcanoes up in that area. So they're at our next highest risk. Going down the very light blue, very lowest risk. So for us here in Florida, we're not anywhere really near any kind of plate boundary, so we're in this very low risk. If you'll notice that first green bit going into yellow up above us in South Carolina, well, that's where I live. I live up near that North Carolina, that green blip there, and we're on an old fault line. And we were in this, you know, moderate risk for earthquakes. We had them fairly frequently, they were just never real severe. Now, tsunamis. So we have volcanoes, earthquakes, tsunami. Then these are all caused by a similar feature, if you will, this tectonic plate action. Now, a tsunami is a series, we tend to think of it being one, but it's usually more than one, series of huge waves. It just means giant wave, if you will. Tsunami is the Japanese term, tidal wave is the English term, if you will. But there are these tidal waves, these giant waves generated when the ocean floor suddenly rises or drops. All of a sudden I get a huge shift in the ocean, and this generates energy. Waves are just energy. Normally waves are caused by wind. Wind's blowing on it and the water piles up and we get a wave. Tsunamis are generated from when something happens at the ocean floor. Either the ocean floor pushes up real quick and I get a wave, or it drops real quick and I get a wave. They can travel several hundred miles per hour, but they slow down as they approach the coastline. Out in the deep ocean, they're pushing really fast, but then they start coming up the shelf. As they hit the shelf, they begin to push up, the energy pushes up, and they begin to slow. Now in December of 2004, there was the Indian Ocean tsunami. I was living in Thailand at the time of this. I had vacationed in Phuket, an area that it got hit. We just weren't vacationing there at the time. We were up in Chiang Mai when this one hit. So it was somewhat personal to, we had been in that exact area. We actually had friends that were very close by. They were able to get inland and they were safe, but they were at ground zero at the time. But this huge Indian Ocean tsunami came in and sweeps through Indonesia, Thailand, this whole area, India as well. There were over 230,000 people died in this single tsunami, and there was no warning system. The only warning system that there was is you started to see the ocean recede. And all of a sudden, oh my goodness, look, why did the ocean go away? It receded because it's getting ready to build up and come in this huge, massive wave. So lots of lives and damage in Indonesia, the southeast coast of India, and then upwards into Thailand. No warning system, had no idea it was coming until it was too late. We knew that there had been an earthquake, but measuring the tsunami, they didn't have any sensors around to know what was happening. In 2011, just 7 years later, there was a Japan tsunami. This is one that killed almost 19,000 people in Japan, and this is the one that damaged all of those nuclear reactors. They needed the power to run the water to cool the reactors. They had protections in place, but so many got hit at the same time, they lost power to the whole region, and they couldn't cycle the water, and the plants began to melt down, creating a huge issue. But once again, 2011, a large one hit there. Now, we can detect tsunamis by placing buoys out in the ocean. And in a lot of areas, we have them. So they can warn people to get out away from the coastline in time. But of course, there's nothing we could do about the power plants. And even warning to get people away, everybody doesn't always listen. We give evacuation orders for hurricanes, and people stubbornly stay in their houses and die every year from it. This happens in the United States, it happens everywhere. It's also some of what happened in Japan. We do have these pressure sensors out on the ocean floor, and we have more and more of them out today than we ever have before. So if you look at the kind of graphic back here it's showing, we put these out on the floor. Once again, the seafloor drops or falls, rises, depending on which, causes a huge wave to form, and that wave travels inland. Once again, they can travel at several hundred miles per hour. So if you get hit by one, you can roughly imagine what it would be like to get hit by a wave of water traveling at 300 miles an hour. The impact itself is enough to kill people. And then of course you're pushed along, and anything you slam into is horrible. And once again, these things can be 30 feet high, 40 feet high. They are massive, and it tends to come in series. It's not just one singular wave, another one comes behind it and behind it. So this one, like in that South Indian, you can see this one where it hit underground in the ocean. So it wasn't the earthquake causing damage, it was the tsunami that wound up hitting all of this area around India, Bangladesh, the Thailand, and Indonesia wound up getting the worst of it, or the brunt of it, if you will. Well, that wraps us up for geological disasters, if you will. Is wrapping up the causes of earthquakes, volcanoes, and tsunamis, all having to do with the tectonic plates. This will wrap it up for chapter 14. Take care, and we'll see you next time.